Okay, welcome back to McNab Chemistry. Today we're going to have a look at using acylation reactions and the nucleophilic addition elimination mechanism to make a carboxylic acid. Okay, so if we react water with an acyl chloride, a carboxylic acid and steamy fumes of HCl are produced. Okay, so the word equation for this reaction is the water plus the acyl chloride makes a carboxylic acid and hydrogen chloride gas. Okay, whenever you do these addition elimination reactions, you always get, with acyl chlorides, you always get steamy fumes of HCl being produced, and that's a giveaway for the fact that the reaction has taken place with an acyl chloride. Okay, so in this reaction the water is the nucleophile. Okay, so there's my water, and that's my nucleophile. If you remember about the structure of water, it's got two alone pairs on the oxygen, so two non-bonding pairs on the oxygen. Okay, and it's one of these electron pairs on the oxygen which attacks the delta positive of the COCl group. So water plus ethanoyl chloride goes to ethanoic acid plus hydrogen chloride gas, steamy fumes of HCl. Okay, so let's just remind ourselves about the structure of ethanoyl chloride or any general acyl chloride. Okay, so the functional group is COCl. Okay, meth eth, I've got two carbons in a chain there, so meth eth is ethanoyl chloride. Okay, and let's just try and remind ourselves why the carbon in the acyl chloride group is more delta positive than a carbon in the equivalent ethanoic acid COOH group. Okay, it's because we've got the presence of this chlorine, so that oxygen is more electronegative than that carbon, so it withdraws electron density towards it, making that delta plus and delta minus. Okay, but that carbonyl group is present in a lot of molecules and these reactions don't happen. Okay, but in the presence of the acyl chloride, because we've got the Cl there which is more electronegative than the carbon and it withdraws the electron density towards it again also, so we've got that dragging electrons that way, we've got this dragging electron density this way, makes that carbon even more delta positive, and it makes it so delta positive that the lone pair on the oxygen can attack that delta positive carbon. Okay, so it makes this nucleophile want to react with the acyl chloride because the alone pair is attracted towards the delta positive carbon because the delta positive is big enough for this lone pair to be attracted towards it. Okay, so remember the C of the C equals O group, remember C equals O group, that's the carbonyl group, is significantly delta positive, big enough for the lone pair on the O of the H2O to be attracted towards it. This is how the nucleophilic addition elimination mechanism begins. Okay, let's have a look at the mechanism now. Okay, so here we go. Meth eth, ethanoyl chloride plus water. Remember, I've got two lone pairs on the water molecule, but only one of them really is attracted towards the delta positive carbon. Okay, so this is what happens to start with. The nucleophile attacks the delta positive carbon and it joins on to that carbon. Okay, this causes a shift in the electron arrangement around this carbon here, so we end up with a single bond there. Okay, and this oxygen has a full positive charge on it. Okay, that's all we need to know for our A level. So that has a full positive charge on there. Okay, right, so the next thing that happens then, this positive charge here influences the electron distribution throughout this intermediate substance. Okay, right, so because we've got a positive there, it causes the electrons to be dragged through the molecule this way. Electrons are negative, we've got a positive here, opposite charges attract, so electrons get dragged through the molecule that way. Right, okay, so when that electron density starts to be dragged through the molecule this way, through the intermediate I should say this way, okay, the electron density when it gets to around this region starts to repel the electrons there. Okay, and it weakens that bond and it causes the Cl to fall off. Okay, it causes the Cl to be eliminated. So this is my nucleophile. It's being added onto that carbon. So nucleophilic addition followed by some elimination, hence the naming of the mechanism. Nucleophile is added onto the carbon and then we eliminate the Cl minus followed by some H plus. Okay, so this is the first part of my elimination. I eliminate the Cl minus and then You can see here that the oxygen has got a positive charge on it, so that attracts electrons from this covalent bond between the O and the H, okay, weakening that bond and it causing the H plus to be eliminated. Okay, now if we put together this Cl minus and the H plus, okay, we put that together with that there, okay, we end up with HCl steamy fumes. Okay, there you go. So that's where our steamy fumes come from. They come from the elimination of the Cl minus and the H plus off that molecule there. Okay, and we end up with CH3COOH. Okay, because of the way the mechanism's drawn, that's the way the product looks. Okay, then we can rearrange that because of our free rotation with our single bonds. Okay, and we'll end up with this CH3COOH, which is ethanoic acid. Okay, so that is the mechanism for the nucleophilic addition elimination reaction. Okay, to make ethanoic acid using water, the nucleophile, and ethanoyl chloride, the acyl chloride. Okay, I hope that's been helpful. Thank you for watching, and don't forget to click on the bell notification to stay fully updated. Okay, thank you.